Okay, chapter 5. We have looked at linear functions, we've looked at quadratics, we've looked at polynomials, rationals, and now we are moving on to exponential functions. And you can recognize an exponential function because you can see that your unknown is in that exponent position. So let's just start and look at the graph of f of x equaling 2 to the x, the equation of that particular exponential function. And to graph anything, we can always make a table of values. So if I were to let me get my pen on here. If we were to let x equal 2, oops, not working here. If we were to let x equal 2, then we know 2 raised to the second power would give us 4. And we have our 0.24 right here. And if x were 1, 2 to the first power would give us 2. And if x were 0, 2 raised to the 0 power gives us 1. If x was a negative 1, 2 to the negative 1 would be 1/2. And if we had x being a negative 2, we would get 1/4, etc. And so as x is getting larger and larger, our graph would be, y values would be getting larger and larger. And as x is getting smaller and smaller, the value of that quantity would be getting closer and closer to 0 without actually equaling 0. So our domain, we can plug anything in. Our domain goes from a negative infinity to infinity. Our range, our y values, well, we're never going to get out 0. And so we're going to have 0 going off to a positive infinity, not including the 0. Our y-intercept, when we replaced x with 0, we got a y value of 1. So our y-intercept is 0, 1. X-intercept, well, that quantity is never going to equal 0. So we do not have an x-intercept. It does not exist. Horizontal asymptote, a line that our graph is approaching, where the distance between our graph and that particular line is getting closer and closer to 0. We have a horizontal asymptote at the x-axis, at the line of y equal to 0. So as x is going towards a negative infinity, our graph is approaching that horizontal line of y equal to 0. Or they would say the limit of that function is equal to 0 as x is going towards a negative infinity. So we are going to be looking at some exponential functions that are in the form of this y equals b to the x, where that base is always going to be something that is going to be either greater than 0 and it's not going to equal 1. So let's look at a couple of different graphs here. So if we go back to our idea of our translations and our reflections, first of all, y equals 2 to the x. We just looked at that graph. Our graph of y equals 2 to the x looked something like that. As x was getting larger and larger, our y values were getting larger, and as x was getting smaller, our graph was getting closer to that x-axis. And we know that we had this y-intercept at 0, 1. If we were to look at the graph on number 2, y equals minus 2 to the x, well, we know that a negative out in front of our function tells us to flip that graph over the x-axis. So if we take our basic graph in number 1 and we flip it over the x-axis, now we're looking at something that looks like that, where if we were to solve for our y-intercept, replacing x with 0, we would get a negative 1. If we look at number 3, our basic graph is that 2 to the x, but in this case we have the negative that's attached to the input, to the x value, and we know that anytime we negate our input, that's just telling us to flip it over the y-axis. So if we take our graph that's in number 1 and we were to flip that over, reflect it over the y-axis, our graph now would be coming down from left to right. And again, our y-intercept would still be here at 0, 1. And on number 4, we take that basic graph from number 1 into the x, and we know again that this negative is telling us to flip it over the y-axis, and this -2 over here is telling us to shift our graph down 2 units. So if we take what we just did on number 3 and shift our graph now down 2 units, our graph would be along here. Now, keeping in mind that we had this horizontal asymptote at y equal to 0, so if everything is shifting down, we would now have our horizontal asymptote down here at y equals to a -2. And our y-intercept, if we were to replace x with 0, we know that 2 to the 0 minus 2, or 1 minus 2, would give us a -1. So we would have that y-intercept at 0, -1. So if we come back up here real quick, where we had our y equals b to the x, anytime that our base greater than 0, if our base is larger than 1, then our graph is going to be increasing, versus if our base is between 0 and 1, some sort of fraction, our graph is going to end up decreasing from left to right. Or here, what we refer to as exponential growth, and over here, what we refer to as exponential decay. And if you look at number 3, over here, number 3 is where our base technically is between 0 and 1, because 2 to the negative x is the same thing as 2 to the -1 to the x, which would be our 1/2 to the x. So anytime your base is between 0 and 1, your graph is actually decreasing from left to right, versus your base larger than 1, your graph is increasing from left to right. Okay. Now recall back when we were working with exponents, when our quantities were equal and our bases were the same, then we knew that those exponent quantities had to be equivalent. So just going back and reviewing that concept, if I have on number 1 here, 3 to the x equaling 81, well, I know that 81 is the same thing as 3 to the 4th power. And if the left side equals the right side, and we know that our bases are the same, then our exponents would have to be equivalent. So x would have to equal 4. On number 2, well, 32, the left side has a base of 2. We could rewrite the right side with a base of 2, and 2 is the same, 32 is the same thing as 2 to the 5th power. And again, since our bases are the same, left side is equal to the right side, then that means that our exponents would have to be equivalent. So 3x minus 4 would have to equal 5, or we would get x equal to 3. On number 3, we have a number of bases of 4 involved here. The left side, we have 4 being raised to the x minus 3. Well, 16, we know is 4 squared. We have our 4 to the 2x. On the right side, recall with our exponents, when you are multiplying like bases, you keep the base the same and you add your exponents. And now again, left side equals the right side, bases are equivalent, which means that our exponents would also have to be equivalent. And combining our like terms, -5 would have to equal our x. Number 4, I'm going to let you try that one on your own. We will move over to number 5. On number 5, left side, we are multiplying like bases, so we know that we would keep those bases the same, add our exponents to combine those together. On the right side, 1 over 27, which is 1 over 3 cubed, and we know if we move a term up, switch it from denominator to numerator, the sign of the exponent would change. And now that our bases are the same, left side equals the right side, we can set those exponents equal. So our 2x plus 1 would have to equal our negative 3, or 2x equaling a negative 4, x being a negative 2. Number 6, I will let you guys try that one on your own after. And we will switch over to number 8. On 8, you have 25 to the 2x plus 1, 20, and on the right side, a 125. Both of those could be rewritten with a base of 5. 25 is 5 squared. 125 is 5 cubed. Recall, if you have a power raised to a power, then you should be multiplying those two. That gives us 5 to the 4x plus 2, equaling 5 cubed. And again, left side equals the right side. We have like bases, which means those exponents would have to be equivalent as well. And we get 4x equal to 1, or x equal to 1/4. And I will leave you to try number 9 on your own after. And we'll switch over now down to example 1, estimating 2 to the 40th power in terms of a power of 10. So, and if we want to switch that to a power of 10, well, 2 to the 10th is approximately equivalent to 1,000. It's approximately equal to 10 cubed. So if we're just trying to estimate, 2 to the 40th would be the same thing as approximately 2 to the 10th to the 4th, and 2 to the 10th to the 4th would be approximately 10 cubed to the 4th, replacing our 2 to the 10th with our 10 cubed, which would give us approximately that 10 to the 12th, because recall, power to power, you should be multiplying those exponents. Just reviewing again our exponent rules when we are working with exponents. On number 2, we're given the function f of x equaling 2 to the x, that exponential function. You should recognize that equation of f at x plus h minus f of x, all divided by h, that difference quotient. So we want to evaluate the difference quotient for that function of 2 to the x. So f at x plus h, our top left, tells us to go to that function, replace x with the quantity of x plus h. So that would be 2 to the x plus h, minus the function itself, which is just our 2 to the x, and then dividing that whole thing through by h. And if we just want to try to simplify that a tiny bit, or rewrite that a little bit, the left side, this 2 to the x plus h, will recall when you are adding exponents, that means that the operation of multiplying of like bases was going on. So that top left is really the same thing as the 2 to the x times 2 to the h minus our 2 to the x. And I have that common factor of 2 to the x that I could factor out, take out, and I would be left with that 2 to the h minus 1 divided by h. Nothing cancels, but just to be aware that this this 2 to the x times 2 to the h is the same thing as this 2 to the x plus h. And that idea could come into handy as we move on to future problems in future sections. I'm going to leave number 3 for you to try and just simplify that one. You should, when you simplify after, you should get 1. And I will let you try that on your own. If we move on to number 4, we're given 2 equations, f of x and g of x. And if we were just to sketch a graph of those, our f of x is our basic graph of 2 to the x, and we know our basic graph of 2 to the x looks something like that. The plus 1 attached directly to the x, recall, is telling us to shift that graph to the left 1 unit. So if I was at the point 0, 1, which was our y-intercept, I would now be over here at a -1, -1. So my graph would be doing something like that. And we know our y-intercept, if I were to replace x with 0, would be 2. So there is our graph of f of x. G of x, 2 to the -x plus 1. Well, recall that the plus 1 is telling us to go left, and the negative attached directly to the x is telling us to flip over the y. And if we take our 2 to the x and we shift to the left first, and then we flip over the y-axis, then our graph would be doing something along those lines. And there would be our g of x. And we can already see in our picture that point of intersection where those graphs are intersecting. So we should already know that our answer is going to be 0, 2. If we go to solve that algebraically, if you are finding a point of intersection, then where are those two? Sorry about that. Where are those two equations equivalent? Where do they have that common value? So 2 to the x plus 1 equaling 2 to the -x plus 1. Well, we know if we are solving and our left side is equal to the right side and those bases are the same, then that means that our exponents would have to equal each other, combining our like terms, bringing our x's to the left and our numbers, constants, to the right. We get x equal to 0, and if I were to go back in and plug that back in, 2 to the 0 plus 1, I would get 2. And that point of intersection, as we already saw when we graphed it, was 0, 2. Our last example here is example 5. We want to solve for x. Well, we know any time that we can take out a GCF, our greatest common factor, that we should always try to do that. And we have this common factor of 2 to the x. So if I factor out my 2 to the x, I'm left with an x cubed minus 3 equal to 0. And we're only going to solve for our real solutions. And we can apply our 0 product property. So either 2 to the x has to equal 0 or x cubed minus 3 has to equal 0. And we know 2 to the x will never equal 0. Recall your 2 to the x graph was that, and that graph will never intersect the x-axis. So here, that is not going to happen. And x cubed minus 3 equal to 0. Well, if x cubed is equal to 3, take the cube root of both sides, and we are going to get x equal to the cube root of 3. So we have one real solution for x, and that is the cube root of 3. And we will hold off here